everybody. Welcome to BSidesSF day number 2. Glad to have you. I know it's still early. You know, I'm still in bed usually at this time. So, welcome. Glad to have you. Glad you could make it today. We got some awesome talks again today. Starting off today. Well, first of all, just want to again thank our sponsors. I can see on all the signs. We appreciate all that they've done for us. One or the other. Want to mention that we have a raffle today at lunch. So if you haven't already, put your business card or name in that. There's a couple of raffles on there. There's one for some Fitbits, one for a GoPro from Palo Alto Networks. Fitbits from Fitbit. The Palo Alto Networks is a GoPro, and we also have some books from No Starch Press. So make sure to go put your name in the raffle sometime before lunch. And you need to be present to win for those. The other thing, let's try to think what else. So feedback. If you have feedback about the conference, you should go to BSidesSF.com/feedback. If you have any feedback about the sessions that you go in, if you're on the schedule, there's a feedback survey button that you can click to provide feedback. Now, this is sedating the watchdog, abusing security products to bypass Windows protection. The two speakers are Tomer Bitton. He has more than 12 years of experience in security research. He focuses on original research such as malware reversing, hostile code, and extreme packers. His prior role, he served as a low-level security researcher at the National Electronic Warfare Research and Simulation Center. There he won an Excellence in Innovation Awards for complex security projects. Udi? Udi. Sorry, I am terrible at names. Udi is CTO of InSilo. He has more than 15 years of experience in security with a proven track record in leading cutting-edge cybersecurity R&D projects. He spearheaded the direction of the cybersecurity unit at the National Electronic Warfare Simulation Research and Simulation Center, and served as CTO. And he's done lots of other things. So let's give a warm welcome to the guys from InSilo.
Thank you.
Okay, so first of all, I'm sorry about the colors. We used a lot of green, and apparently it doesn't show that well. So let's start. You heard enough about us, so I'll just continue. So today we're gonna talk a lot about function hooking, more specifically inline hooking. We'll talk about the research we did and exactly how those things work, how hooking works. And then we talk about injection techniques and some security issues we found. We'll do a demo to show that it's actually a real issue. And then present some security tools that we've written to do this research. So just a few things about hooking. So generally, the purpose of hooking is to intercept API calls and augment their behavior, change the things they do. Almost every security product out there uses hooks in some way. I mean, anti-exploitation tools normally hook all kind of memory function and post-related functions to detect exploitation. Almost all AV products use hooking, and personal firewalls, Commodore, and Zone Alarm, all of these. It's also used a lot in non-security products. A lot of application performance tools use hooking to monitor the time it takes to functions to execute and things like that. And also Microsoft application virtualization technology does that. Citrix do it. A lot of products use it. And malware does it as well, mostly for main the browser techniques. So what we did in this research is that we took about a dozen security products and we checked out the implementation of the hooking mechanism, the hooking engines, the way they inject. And from now on, I'm going to talk about hooking engine, which is usually the DLL that the security products inject into the product. And we also talk about Kernel-To-User DLL injections because these are the techniques that are usually used to get this hooking engine into the processes which are being monitored by the security vendors. So hooking on 32-bit processes is very straightforward. I mean, it starts off normally by disassembling the few first instructions of the function prologue, then allocate some code stub in memory, copy the prologue instructions to the code stub, and then patch the prologue with a jump instruction to the hooking functions, which later can use the code stub to call the original function. So these are a few snippets from WinDBG of the way it works. So this is an example of Internet Connect function before it is being hooked. You can see it in the upper side of the screen. It has pretty much regular prologue, the move VDI, push EBP, and setting the stack frame. And after the hook is set, these instructions are replaced with a jump to the function that hooks that function. So if we follow the instructions on the hooking functions, we can see that there's a call to the code stub. In this instance, the hooking functions starts by calling it, so this is why it's in the start of the function. And we can see the copied instructions in the code stub, and followed immediately with a jump to where the code of the original function continues. So normally 32-bit hooking should be straightforward, but there are other techniques like 1-byte patching, just setting some kind of illegal instruction or breakpoint instruction in the beginning of the function and setting an exception handler to catch that. This is usually, I guess it's only done by malware. I've never seen a legitimate hooking engine that does that. There's also a hot patching mechanism of Microsoft that they use to enable patching of security vulnerabilities without needing to update the DLLs. So the way it works, instead of replacing the entire prologue, you just replace the move VDI instruction that you can see in almost every API call in Windows with a short jump. The short jump leads to a far jump, which is located right above the function prologue. However, there are some possible complications when trying to hook, even in 32-bit. So these are just a few examples. One of them is when in a case where we have a relative jump or a relative call in the first few instructions of the function. This means that the hooking engines must fix the instructions after copying it to the stub, because since the instruction will reside in some other address, its target must change accordingly. This normally happens when two hooking engines trying to hook the same function. Another issue that can happen is that you try to hook some very short function. Let's say some function that just returns 0, so sorry AX, EAX, and ret or something like that. And then you don't have enough bytes in the function to set the long jump. So sometimes it's not really possible to make this kind of hooks, at least not with the normal method. And sometimes you can just disassemble afterwards and see that these instructions are not being used. The third issue here is a bit more complex, and what actually could happen is that some jump inside the function leads to the prologue of the function. Not even the first instruction in the prologue, just let's say the second instruction or the third instruction. And the problem is that when you patch the prologue, it will create illegal instruction for the jump. Now, as far as pretty much every hooking engine I know doesn't really know how to handle this kind of function, and even worse is that in order to detect that the problem exists, you have to disassemble the entire function because you can't tell just by looking at the prologue if this exists. The good thing is that it's extremely rare, and it, as far as I know, never happens on regular exported functions. Continuing to 64-bit hooking. In 64-bit, the things are a bit more complex because you can't get anywhere you want just with 5-byte jump instructions, since it's limited to 2 GB range. So the process is a bit different. Start with disassembling the prologue, then you usually allocate some kind of trampoline code and the code stub. You add a trampoline, which is usually something like move absolute address to RAX register and then jump to RAX, and copy the prologue instructions to the code stub and patch the prologue with the jump. And when the jump leads to the trampoline, and that's one way to solve it. We can see in this example exactly the way it's done. This time it's Internet Connect A. So before the hook, we can see the prologue. After the hook, it was actually, in this case, the hooking engine patched 10 bytes from the function, though it could probably did it in only 5. So there's a jump instruction to some code stubs, which is pretty close in address to where the function resides. And we can also see there's some kind of pop instruction over there, which I'll explain in a minute. And the trampoline code, which is exactly what I showed before, which leads to the actual hooking function. So if we follow it the same way we did in the 32-bit, we'll get to the code stub, and we can see that there is an extra push RAX here. That's to accommodate for the pop, which follows. So this is pretty simple as well. There are other techniques to make to achieve this. One nice technique is to push a 32-bit address and then return. This only takes 6 bytes, and its only requirement is that the hooking function will be in a 32-bit address, or that if you're able to do it, just put a trampoline in a 32-bit address. Another technique which preserves all registers, the format of techniques I showed don't preserve all registers because it has to use RAX in order to do the jump. So that's a nice technique by Nikolai. The way it works is by pushing a 32-bit value to the stack. Because it's a 64-bit machine, then 8 bytes are going to be allocated on the stack. Then push the high D word, set the high D word in the stack and return, which is absolute jump to 64-bit address without changing any register. The complication in 64-bit hooking is pretty much the same like in 32 bits. The main difference is that there are much more instructions which are relative to the location of the instruction, because 64-bit assembly supports RIP plus offset addressing. So those need to be handled as well by the hooking engine. So just a quick recap. The inline hooking is probably the most common method used in real-life products. It's rather intrusive and exists in most endpoint products. So you can follow those links to read more information about hooking.
Hey guys. So kernel injection techniques. Kernel injection techniques mainly used to inject DLLs from the Kernel-To-User mode processes. It's also very common in sandbox escape shellcodes after a successful exploitation of a privilege escalation vulnerabilities, and also to inject code to protected processes. There are much less technique than user mode injections, and it's much less documented than the user mode one. It's used both by malwares and security vendors. The user APC is the most common kernel injection technique used. It's used by several malware families like zero access, like TDL, and as I said, also in sandbox escape shellcodes, and very common in security vendors like antiviruses like AVG, Kaspersky, and also application performance and application monitoring products. Searching Google, you can find a very well documentation on the technique, and also some leaked source code, mainly for malware samples and families. So basically, it's very easy the implementation is very easy. All you need to do is register a load image callback using a notify routine. Then you need to write a payload that will load the DLL using the LDR, load DLL, or load library functions, and then use the APC function, the initialize and the insert QAPC routines in order to get code execution. So this is how it looks like from a leaked source code of TDL. So in this function, basically, we set the load image callback. You can see the function circled in red. After that, this is basically preparing the payload. This is the DLL which will be injected to the target process. Here you can see that the virtual alloc basically from the kernel. So allocate the memory inside the target process. And then you can see the str copy basically copying the DLL from the disk to memory. And the last section is using the initialize and insert QAPC routines in order to get the code execution. If you check on the right side, you can see the load library and the in-memory parameters and the in-memory DLL as the parameters. Entry point patching, it's a very interesting technique. It's not very common, but we think it's very interesting. It was first, as far as we know, it was first used by Duku, by the Duku malware. You can find here the link. You can go inside. There is a full documentation of the malware and the technique. So the implementation is very easily. Basically, you need to set a load image callback using the notify routine and wait for the main module to load. Once loaded, you need to write the payload inside the target process. And then you need to replace the image entry point with a jump to the payload. Once the payload executes, all you need to do is basically restore the code of the original entry point and jump to the OEP, to the original entry point, the second one. So this is how it looks like in a patched Internet Explorer. If you check on the left side, you can see the jump instruction. This is basically the code this is the patch function. And if we take it from the right side, you can see there is a jump. If you follow the jump, you can see the function prolog, the push EBP, etc. And then there is another jump. So if you follow the jump, you can see it's circled in red, the first one. There is a combination of the load library and memcopy functions. Basically, it will load the DLL. This is the hooking engine. In the middle, there is a use of the memcopy routine in order to restore the original bytes of the entry point. And at the bottom, there is a jump to the OEP, to the original entry point. Import table patching, it's another very interesting technique. As far as we know, we were the first one to publish it last year in BSides Las Vegas. Before that, it was undocumented. As far as we know, it was never used by malwares, only in security vendors, like Symantec, like Trusteer, and the Microsoft AppV. A very similar method of implementation can be used, the TLS data directory instead of the import table. So let's see how it looks like. So again, you need to register a load image callback using the notify routine and wait for the main module to load. Once the main module was loaded, you need to allocate the memory inside the target process for the new table. And then you take the old table with the new row, the new record inside, and copy to the new allocated space. You need to point the import directory RVA to point to the new table. And once it's done, once the DLL is loaded, all you need to do is fix basically the RVO of the import directory to point to the old table. And the DLL is loaded. So this is how it looks like in a patch to Internet Explorer. On the left side, you can see that the import directory RVA is basically pointing outside of the image. And on the right side, you can see the new row that was added to the table. This one, we call it NTDLL-User32 patching technique. It's a very interesting one. It's used only by security vendor. We saw it a few months ago. The technique is basically based on, again, register a load image callback using the notify routine, and we need to wait for NTDLL to be loaded. Once NTDLL is loaded, we need to write the payload to the target process. Once it's done, we need to replace the prologue of LDR load library with a jump instruction. Basically, the jump will point to the payload. And once the payload is once the DLL is loaded, the payload is loaded, you need to restore the original bytes of the NTDLL.DLL and jump to it. So this is how it looks like in a debugger. I know it's hard to see, but believe me, this is a patch function from user32-DLL. There is a move address to EAX and then jump to EAX. So once the jump is done, we can see another jump. You have a few nopes and then another move address to EAX and then jump EAX register, and then you jump to the payload. Inside the payload, you have a load library, which will basically load the DLL of the antivirus in this case from a full path. So a quick summary. So kernel injection is mainly used to inject DLLs from the Kernel-To-User mode processes. Very common in antiviruses and security products, and also in malwares. For security products, this is the way they load the hooking engine. Basically, this is the DLL in order to intercept and do whatever they need inside the process memory. Because of the complexity of the implementation, they are prone to lots of mistakes.
Okay, so what we did is to look for possible security issues in the way these things are implemented. So we saw about 6 issues, and the first one is unsafe injection methods. So some of the implementations, instead of loading a DLL from absolute path, use the relative path to the DLL. This means that an attacker can just put his own DLL in the target in a hooked process folder, and the security product will load the attacker's DLL instead of his own DLL. This is a classic DLL hijacking attack, and it's a nice way to gain persistency because and to disable the specific security vendor in the specific process, because each time it loads, the security product will not load and the attackers will be there. Another issue that we saw is that this was only one vendor, and it's a bit weird that they chose to do it, but they put in the app data folder under local vendor the DLL that's been injected to every process in the system, and it was not protected in any way, not by a driver, not by permission, no protection at all. So this also can be easily replaced by an attacker and be used to get consistency on the machine. So we think that has quite high severity because it's so easy to do those things, and it's a bit negligence by the vendors that these things can happen. Another thing that's quite severe is that it happened at least in 2 vendors that we saw, is that the Kernel-To-User injection mechanism allocated in a constant address, writable and executable memory, which means that it practically bypasses Windows protection. I mean, ASLR can easily be bypassed because those code stubs normally contain pointers to critical OS functions, for example, LDR load library, memory functions like anti-virtual allocate memory, anti-virtual protect memory, all these functions. So an attacker can directly call these and and use it. So ASLR is pretty much meaningless in this case. And the attacker doesn't really even have to allocate his own code stubs in memory, because he can just reuse the writable code stubs that the vendor set up for him. So it makes exploitation much, much easier. All you need to do is to write to a constant address the code and find a way to jump to it. If this place contains hook stubs, so overwriting some hook stub means that the next time that this function is going to be called, the attacker's code will execute. This is a really bad issue. Another thing that we think it's quite severe is to allocate code at a predictable address, even if it is not writable. The reason that it's problematic because it still practically bypasses ASLR. The attacker can normally bypass the hooks. So, because all it needs to do is to call the code stubs, and in all the cases we saw, they were on constant offsets, which means that in order to, let's say, bypass some anti-exploitation vendor that hooked, let's say, virtual protect function, all you need to do is to call the offset in his code stubs. To call the functions and completely bypass the protection. And also some of the code can also be used as part of a rope chain. Normally the rope chain can be really simple because you already have all the functions you want in a constant location, so building it is far easier than in a normal scenario today. The next two issues are a bit not that severe, but still exist, and that's leaving the code stub themselves writable and executable. So an attacker that gained the ability to read and write from arbitrary memory can probably use that to bypass control flow guard in Windows by just overwriting the hook stub and then causing the function to execute. Because control flow guard allows the attacker to call functions prologues, so it will just execute the attacker code. Generally, we don't think it's that much of an issue because attackers that was able to get arbitrary read and write will probably succeed to execute code anyways. So, but still, we don't think that security vendors should add issues to add possibilities to the attacker. And another thing that we saw, which was a bit surprising because we didn't even look for it, is that some vendors leave the actual hooked functions as writable. This is not that significant as well because it can probably be used only to bypass CFG or something like that. But it probably shows a bit laziness by this kind of vendors because restoring the protection on the page is just making another call, and apparently some of them don't do that. And that's pretty much it. So now we're going to go on to see a demo and the way it can be exploited in a real-life scenario.
Okay, so let's see how it looks like. Perfect. Okay. So hopefully you will be able to see everything. So what I have here basically is a Windows 7. I have one of the top 5 antiviruses installed here. So let's see the vulnerability basically. Let's open a user mode process. Let's take Adobe for an example. You can see it, right? Okay. Let's open Immunity Debugger. Let's attach to the process. Great. Okay. Let's go to memory. And we have it here. You can see basically this is the address. Yeah, I know it's a problem, but again, believe me, this is the address that was basically, this is the code stub that was injected from the kernel. So it's on a constant predictable address. The permission is read, write, execute. So basically what I have here, I have a full page. Let's go inside, and you can see the stub. Okay, so you can see the stub at the top, I don't know, a few bytes, and then you have a full page, read, write, execute. I can go down, and you can see that I have lots of space. Basically what I need to do is just take my shellcode, copy to this space, and I can override the stub of the antivirus if I want. If not, just copy it to another offset, and then jump to my payload, and we are done. So let's see how it looks like. So I have the PDF. Let's give it some execute. Okay. Let's open a PDF file. Okay, I have it here. Let's put a breakpoint when a new DLL is loaded, so we can see the rope chain. Break on a new module. Okay. Let's load the DLL. Okay, we need to wait basically till ICU-CNV, this is the DLL we took the rope gadget from. So let's wait till it will load. It will take a few seconds. I guess you can't see the name. Okay, I think in the 2 DLLs. One more. Okay, and another one. Okay, so ICU-CNV basically is loaded. So let's go to CPU. Let's put a breakpoint on the first gadget, and we have it here. Okay, let's give it to execute. Another DLL is loaded, and the breakpoint was hit, so we are on the first gadget. Let's step inside, second gadget, third, another one, and this is the most interesting. This is the rep instruction. So basically right now I'm taking my shellcode and copy it to the allocated space of the antivirus. So I have it here. Let's go and follow the address in the dump. So you can see it at the bottom. If I will go up, you can see the stub. This is the stub of the antivirus, and again I have a full page. So I didn't want to override the stub, so I wanted to be nice. So let's give it. Let's put a breakpoint after the rep. Okay, and you can see the shellcode at the bottom here. Okay, so let's give a few instructions. Another one, another one, another one, and I'm inside the shellcode. Let's give it an execute. And I have the calc. So basically what we did, there was a predictable read, write, execute page, a full memory page inside a user mode process. It was allocated by one of the antiviruses that I have it. So again, full page, just took the shellcode, few rope gadgets, copied the shellcode inside the memory, and executed. Let's switch back.
Okay, so just a small recap of the things we talked about. There were about 6 security issues that we saw, and in different hooking engines. And for this research, we developed a few tools to make it easier for us. I mean, debugging each hooking engine is and installing each of the vendors is pretty time consuming, so we tried to automate it as much as possible. So the first tool we wrote was meant to find places in memory which is readable, writable, and executable. You can get this tool in a website, and well, it's pretty simple. All it does is to compare memory maps of processes. I mean, you just open Internet Explorer, take all the places in Internet Explorer where there was executable, writable memory, and then compare it to another instance of this process. To be 100% certain that the issue exists, you should usually reboot the machine. This is the way we solve these issues. Another tool that will be released shortly is a tool to scan for hooks in a process and try to track the code in the hooking function as best as we could. It's like a best effort. I mean, to detect hooks, what we did is to compare the in-memory image to the on-disk image. So whenever we found an exported functions with some kind of diff in the prologue, we started to try to trace this code and get all the related code chunks. And we also checked for each of these functions if the code of the function itself is writable and executable, and then you get a nice table of potentially unsafe locations. There's also a bit manual work. I mean, you have to do it a few times to find constant addresses, to find issues like predictable memory locations and things like that. That's pretty much it. So just to sum things up, so almost every vendor has this capability, and one of the funny things that we saw is that most of them implement their own hooking engine from scratch, and that's a bit weird because there are a lot of open source engines out there, and there are also commercial hooking engines out there, and still each vendor try to develop his own hooking engine and his own kernel injection methods, which probably the reason that most of these issues exist, especially things like we saw in the first issue with the unsafe injections. I mean, those are issues that are known for years now, and doing that just means that the vendor pretty much neglected this entire aspect of the injection and hooking into the processes. Generally, we think that when vendors do complex and intrusive operations, they should also do some kind of security audit for this, because some of the things were really easy to find and some of them were surprising. I mean, when we started this, we never expected to find something like predictable, readable, writable, executable. This is clearly a bad practice which pretty much bypasses lots of mitigations that Microsoft worked hard to put in the operating systems. We also found issue in almost every vendor we tested. I mean, the only reason that we're not mentioning names right now is because not all of the issues that we've seen are fully patched. Most of them already are. Most of the vendors were also very cooperative, and the work was working with them was great. But the funny thing was that on some of them it was quite clear that the security research team is not part of the process, and probably only the development team was part of the process, because on at least 2 or 3 of them we got the same issues after they gave us patches to retest. And so, for example, for the predictable, writable, executable code, we got a patch, and they just removed the writable bit from the location. So you still had a place you can reuse code and bypass SLR with. So the clear solution to this kind of thing is to just free the memory after you finish the injection. There is no reason to leave it there. And it still took 3 cycles until it's totally worked. And this happened with several vendors. So that's pretty much it. We're going to release all the details and all the the things that are kind of missing right now in a few days. And if you have questions, now is a good time. Thank you.
You have a question?
I'm sorry, I can't hear what you're saying.
Me as well.
I understand that your tool is for research, but I was just wondering, do you do anything tricky to see if people are rejected from the process?
If someone injects the tool itself, actually the tool scans itself, but so unless someone tampered with its code, it's supposed. Okay, sorry. So the hook scans itself as well, but so if it was hooked, it's on its own, so it should be detected. But it's not something we really put a lot of effort into. So. Okay.
Thank you.
Thank you.
I want to thank our speakers. Appreciate it. And again, on behalf of Security B-Sides and Fitbit, we want to present you with these Fitbits.
Thank you very
Thank
much.
you.
Udi.
Thank you so much. Sorry about the pink screen and the other.
No worries.
Worked okay.
Yeah, we are good. This is
Cool.
yours. Yeah.
So.